let's start by doing a problem. Find all critical points and classify them as local maximum, local minimum, or neither for the function f of x equals 5 arctangent of x minus 2 log of x squared plus 3x plus 6. So when we see words like classify them, that means we're going to pull out a test. And right now, pretty much the only thing we have is the first derivative test. So all right, let's think about what we can do. Well, we have this function. The first thing you might ask is, where is this function defined? Certainly the arctangent, it's a great function. It's always defined everywhere where we can plug stuff in. That's not a problem. What about this x squared plus 3x plus 6? Is that defined everywhere? How can we tell? Well, there's sort of two things you can try. Now we know for natural log, as long as what we plug in is positive, life is good. So what we can ask is say, okay, what can we say about x squared plus 3x plus 6? And there's sort of two things we can do. One thing we can do, we write x squared plus 3x plus 6. Of course, we have a suspicious gap here. We say, well, what goes in the gap? Well, what we'll do is we'll take the x squared plus 3x and we say, what would we need to add to complete the square? If you take the 3 and divide it by 2, that would be 3 halves. If you square it, you'd add 9 fourths. So that would make the first part a perfect square. Then you could subtract 9 fourths. And now, the first part, that's the square, x plus 3 halves squared. The last part, we get 24 fourths minus 9 fourths is 15 fourths. Now the important thing is, this first part is always greater than or equal to 0. And 15 fourths, that's definitely greater than 0. So the whole expression will always be positive, and therefore, what we plug into log is good. All right. Now what if you didn't do that? What's another thing you could do? Well, an alternative is to say, well, let's look at x squared plus 3x plus 6 and say, our problem comes if we ever hit 0 or go below 0. And so we could say, well, when does it hit 0? So in other words, what are the roots? Now, we can try to factor. I don't think we can, but we can definitely do the quadratic formula. You know, negative 3 plus or minus square root of b squared, which is 9, minus 4ac, minus 24, all over 2. Now, looking at this, I can't help but notice we have a square root of a negative number. And that feels like it might be a little bit complex. Well, in particular, that says we never hit 0. And if we never hit 0, well, we can never cross below 0. Because a continuous function, I can't jump down to a negative unless I go through 0. And it's certainly positive. It's positive at x equals 0. So this is fine. So that says this function is good to go. We are happy with that function. All right. So now we have a function which we know is defined everywhere. And we say, all right, well, how do we classify local max, local min? Well, the answer is we look at the derivative, because critical points happen when there's either a boundary, no boundary here, or when things involve the derivative. So we take the derivative, f prime of x. Well, 5 is 5. Now when you take the derivative of arctangent, it's 1 over, so there's really a 1 upstairs, 1 plus the inside part squared times the derivative of the inside part. In our case, the derivative of the inside part is 1. For natural log, what do? Well, you take 1 over the inside, so you get x squared plus 3x plus 6 times the derivative of the inside, which is 2x plus 3. All right, so there we go. There we go. Now, is this ever undefined? Well, the only possible problem would be if we divide by 0. But again, we know this part, we can see it can't be 0. And this part, we've already talked about, that can't be 0. So life is good. Now, that says really the only thing left for us to do is set it equal to 0. Now, one thing we could do is just actually solve for it equals 0, move stuff around. I tried that once, and it worked. But the problem is, remember we have to come back and use the first derivative, and so we want to make sure our first derivative is written in a very nice, clean way. So before we set it equal to 0, what we should do is clean up our derivative. So if you're going to use something later on, it pays to clean it up. So let's see what we can do to clean it up. Well, first thing we can do is let's clean up this denominator. If we square that, it would be x squared minus 4x, then there'd be a plus 4, we already have a plus 1, plus 5. Over here, minus, I'll multiply the 2 through, 4x plus 6 over x squared plus 3x plus 6. Now, at this stage, what can we do? Well, we can get a common denominator. So you multiply the first term by the x squared plus 3x plus 6, and the second term by the x squared minus 4x plus 5. So if you did that, we'd have 5 times x squared plus 3x plus 6 minus 4x plus 6 times x squared minus 4x plus 5, all over the two things multiplied together. So x squared minus 4x plus 5 times x squared plus 3x plus 6. Now, we're just patient. The first term is easy to simplify. You just multiply the 5 through each piece. So we get 5x squared plus 15x plus 30. Then we're going to subtract. What do you do for the second part? 4x plus 6 times x squared minus 4x plus 5. Well, what you want to do is you want to do FOILing. Well, how does FOILing work when it's more than two terms? Now we can try to understand the philosophy of FOILing. See, FOILing says you want to take one term from the first part and one term from the second part. So FOILing says, take the first terms, the outer terms, the inner terms, the last terms. But it's always the same idea. One term from here, one term from there. So, that means we're going to have a whole bunch of terms. We're going to have 6 terms in total. Well, here we go. What are they? Well, the 4x times x squared, that'll be, be 4x cubed. 4x cubed. Then we're going to have the 4x times the negative 4x, so that'll be minus 16x. Then the 4x times the 5, that'll be plus 20x. Then now the inside parts. 6 times x squared, that'll be 6, I wrote 20x. Should just be 20. Whoops. Double check. No, 20x is right. It's the 16x squared. That's right. Triple check. Okay, good. All right. And then we have 6x squared. Okay. 6 times minus 4x, that's minus 24x. And then 6 times 5, that's 30. Okay. All over that denominator. X squared minus 4x plus 5. X squared plus 3x plus 6. All right. Good. I think we're back on track. Now, let's group terms together. So upstairs, it's polynomials. So downstairs, same expression. It always was. X squared minus 4x plus 5 times x squared plus 3x plus 6. Now, let's see. What do we have? Well, we have a cube. So there's only one term with the cube. Minus 4x cubed. Now, how about the squares? Well, we have a 5x squared. There's a minus 16x squared and a plus 6x squared. If we put those two together, that would be minus 10x squared, but minus makes plus. So it would be the same as 5 plus 10, or 15x squared. How about for the x's? We have 15x there. Here we have a 20x and a minus 24x. If we put those together, that would be negative 4x. Again, we're subtracting, so that becomes a plus 4x plus 15x makes plus 19x. Last part, 30 minus 30, 0. Gone. Nice. Now, well, that's rather convenient. Everything has an x involved, so we can pull that out. So, in fact, let's pull out a negative x. So negative x times and we'll have 4x squared plus 15x plus 19. All over, wait a second, is that plus 19? Let's double check. Just want to double check. Alright. All over x squared minus 4x plus 5 times x squared plus 3x plus 6. And see, the problem I made is I forgot to factor out the negative. So this should actually be a minus 15x and a minus 19. Remember, if you're going to pull a negative out of one term, you got to pull them out of all the terms. There we go. Okay, so now all that's left is we have to factor 4x squared minus 15x minus 19. If it can factor, can it? I don't know. Maybe, hopefully. Now, how do you factor such a thing? Well, there's a couple things you should do. So when you're factoring, you should try to look for some common roots, because that can help. So what are common roots? Well, in particular, I would say you should always try the following three: 0, 1, and negative 1. Now, how do you know if you have a 0? Well, the answer is, if there's no constant term, you have a 0. So see how we started at x? That means we could pull an x out. So that 0 was a root. In fact, we don't even think about it. Well, that's actually what we did, is we said, oh my gosh, 0 is a root. I can factor out an x. How do you know if 1 is a root? Well, you know 1 is a root if you can add up the coefficients and add to 0. So if you take 4 minus 15 minus 19, no, that's not going to work. But negative 1 is a root if whenever it's an even, you add, even power. If it's not a power, you subtract. So it'll be 4 minus 15, so that's plus 15. 4 plus 15 is 19, minus 19 is 0. So that says negative 1 is a root. Now, how do we use that? Well, once you know that negative 1 is a root, that gives you nice information. In particular, it tells you the following. It says that x plus 1 has to be a factor. And once you know one factor, the second factor is a freebie. Say, okay, I have to get 4x squared. X times what gives me 4x squared? The answer is 4x. Then you have to say, I got to get negative 19. 1 times what gives me negative 19? The answer is negative 19. And now we're done. Now you're probably saying, okay, well that's great. What if that doesn't work? Well, then you start doing what you would normally do. Things such as, how can you break 4? 4 can break up into 1 times 4, 2 times 2. 19, there's only one choice. 19 is a good number. It's what we call a prime number. 19 times 1. Then you start playing around. Now we go. Here's our derivative, simplified in all its glory. Set it equal to 0, and what do we see? Well, the critical points are as follows. So we're making a list of critical points. 0, negative 1, and 4x minus 19. When I solve that, you get 19 fourths. Now 0, you probably would have guessed to check that. Negative 1, not too surprising to check that. 19 fourths, nope, would never have guessed that one, but we don't have to guess. We've got math. Math helps us avoid having to guess, which is good. So we found the critical points. We've essentially done the first step, but remember there's a second step, there's the classify. So for the classify, we have to draw them. Draw the number line. We've got to put negative 1, 0, and 19 fourths. It's a little bit over here. It's about 19 fourths. I mean, if you wanted to write it down in decimal, 4.7500 for all those engineers out there who want a couple digits of accuracy. So it's a little less than 5, but it's more than 4. All right. Now, what do we do? Well, we just start picking numbers. And remember, we're only after the sign. So, if I pick, say, 1, that's a convenient number. It's between 0 and 19 fourths. The downstairs will always be positive, so I just have to look at the upstairs. So there's already negative. The x and the x plus 1 are both positive. 4x minus 19 is negative. So if we put those together, that tells us that our derivative, f prime, is positive. On the other hand, if I pick something big like 100, Well, negative, but x and x plus 1 and even this 4x minus 19 are all positive. So that tells me that my derivative is going to be negative. Between negative 1 and 0, say negative a half, the x will be negative, but the x plus 1 won't be negative yet. And the 4x minus 19 definitely negative. So there's three terms which are negative, which means that we're going to flip sign. And finally, if I pick a number like, I don't know, minus 100, it's negative, and that's very negative. And so there's four negatives, making it positive. Now, one thing you probably will say is like, oh, we're flipping signs as we come along here. And the reason we're flipping signs is because notice how all these are like x to the 1, x plus 1 to the 1, 4x minus 19 to the 1. Whenever you have just to an odd power, what happens is that means you're going to cross through. So you're going to go from positive to negative or negative to positive. If it's an even power, that's going to be a time when you come and touch down, but you don't cross through. So you should essentially say, oh, look, I know I'm going to have to flip the signs at 0 and at negative 1 and at 19/4. So once I know where one of them is, I can predict the rest. Now, if it's not so obvious, we plug it in. So we're getting close. But the last thing is, what are they? Well, we look at the behavior. We're positive, and then we're negative. And then we're back to positive again. And then, of course, later on here, we're positive, and then we're negative. And so now, we can just sort of read off the answers. If we're going up and then down, that tells us that negative 1 is a max. It's a local max. It's not necessarily the largest max. 0, going down and then up, which means that 0 is a min. 19/4, we're going up and then down, and that means this is a max. Now, these here, we know these are local, in the sense that whenever we do a test involving derivatives, it always tells us local behavior. It doesn't tell us global behavior, local behavior. Well, what if we wanted the absolute max? Could we make a decision? Well, the answer is the absolute max has to occur at one of these two places. How do we know that? Well, we know that for the following reason. I can say that this value at negative 1 is the biggest value between minus infinity up to 0. The largest I get is at negative 1. Because I'm going up from negative infinity to negative 1, and going down from negative 1 to 0. It means I have to max out in that interval at negative 1. Now, how about from here? Well, from 0 up to infinity, I have to max out at this point, 19/4. Why? Well, because from 0 up to 19/4 I'm going up, and from 19/4 to infinity I'm going down, and therefore the largest point is at 19/4, which means the absolute max is one of either f of negative 1 or f of 19/4. Now, I don't know which, but I can be confident that that's the answer. Actually, I do secretly know which. It turns out it's this one. But you would probably never think to check 19/4. But again, we don't have to. We don't have to think about how to check because we've got calculus. Oh, what a wonderful thing we have. We are lucky people. Lucky, lucky people. Okay, so what's our goal for today? Well, last time we talked about the first derivative, and as a hobbit might say, we've had one derivative, yes, but what about second derivative? Okay, so what about the second derivative? So that's our goal for today. What do we get from it? How do we talk about it? And what can we do? Now, how do we understand the second derivative? Well, let's think about what the first derivative tells us. See, the first derivative tells us about our function. And it tells us whether our function is increasing or decreasing. So what does the second derivative tell us? Well, the answer is that the second derivative tells us when is the derivative increasing or decreasing. And it kind of makes sense because we think of the second derivative as being the derivative of the first derivative. So what can we get from that? Well, So we can say the following. Suppose we have that our second derivative is positive. Well, that can happen. That corresponds to when f prime is increasing. The if and only if arrow is a little bit stronger than what's actually true, but it's certainly true that if f double prime is greater than 0, then f prime is increasing. And we call that concave up. Concave up. So you can kind of see the shape would look like this. And if you just draw in a couple tangent lines, so a tangent line over here has a negative slope, then it's becoming less negative, and then eventually it's zeroing out, and it's becoming more positive. So our tangent slopes are going from negative to positive. That's increasing in value. If f double prime is negative, well, that says that our derivative is decreasing. We call that concave down. And again, if you draw in some tangent lines, see initially we're positive, then we level off. Okay, so that says we went from a positive to 0, that's a decrease, and then we're starting to be negative. So again, we're going, our tangent lines, the slopes are decreasing. So in some sense, we can think about it as saying that our second derivative is telling us something about the behavior of the curve. All right. So here's one way to think about it. So let's just pause for a moment and say, what's happening? Well, suppose I have a point A and I have a point f of A. So here is the point. And now, what do we have? Well, we have the tangent line. So here's the tangent line to the function. That's not the function, it's just a tangent line to the function. Now, the way you can think about concave up and concave down, and I think this is very intuitive and it does help to understand things that are going to come, is that we're concave up if the curve goes up from the tangent line. So this would be concave up. So we are sort of pulling up from the tangent line. And concave down would be if we were on the other side. So concave down says that we actually have the function pulls down from the tangent line. So it's very convenient if you remember that idea. Concave up, we go up above the tangent line. Concave down, we come down from the tangent. It doesn't matter what the slope of the tangent line is. Positive, negative, 0, it's always the same. So in some sense, the concavity is giving us more information about what the function is doing. It's telling us, hey, our function is behaving in particular ways. Let's use that information to see what we can state. And you might say, well, can we use that information, for example, to get better estimates? We'll talk a little bit about that by the end of the session. All right. Now, what if concavity changes? Because we said, well, you could be going from increasing to decreasing. We could be going from concave up to concave down. When can that happen? Well, it can happen if the second derivative is 0 or if the second derivative is undefined. It's the same type of behavior that we saw before. So let's find the inflection point, or possibly points, for the following function. Y equals x cubed minus 3x squared minus 9x plus 15. So we want to look at the second derivative. So we'll look at the first derivative. That's 3x squared minus 6x minus 9. And for now, we don't need to worry about the points where this is equal 0, because we're going straight to the second derivative, because that's telling us about concavity. 6x minus 6. Is this ever undefined? No. It's a beautiful function. It's a great function. So now we say, well, is it ever 0? And it is. That would happen when x equals 1. Now, is that an inflection point? Not quite. This is a potential inflection point, because it's a place where the second derivative could change sign, but it doesn't necessarily have to change sign. We already have a term for critical points. We don't really have a name for potential inflection points. So we'll just say, okay, it could be an inflection point at 1. But how do we check? Well, we say, okay, we'll mark a line. Here's 1. And we pick a value above 1, say, I don't know, 2. Plug it in. 12 minus 6 is positive. That says the second derivative is positive over here. And then we pick a value below 1, say 0, we get negative 6. It says second derivative is negative, which means that below 1, this curve is concave down. And then above 1, this curve is concave up. And therefore, this point 1, that is an inflection point, because we switch concavity at that point. All right. Well, let's try another one. Find the inflection points on the curve y equals 2x to the 6th minus 6x to the 5th minus 15x to the 4th plus 103x minus 83. Now we're like, 103, that's not looking too promising. But we continue, we persist, and we'll see what we get. So, take our first derivative, y prime. Well, that would be 12x to the 5th minus 30x to the 4th minus 60x to the 3rd, and then plus 103. 83 goes away. Second derivative, we get 60x to the 4th minus 120 x to the 3rd minus 180 x to the 2nd, and now the 103 goes away. Okay, so what is that telling us, by the way? Well, that's telling us that we know that if we do this shift up and down, that doesn't really affect the function in terms of like increasing, decreasing. And now, of course, it doesn't affect in terms of concavity. Turns out that the plus 103x, it might affect the function in terms of increasing, decreasing. It's kind of almost like you're doing a shift. That's a shearing action is what you're doing when you add multiple of x. But the shearing action will not affect concavity. So that's good. So that goes away. So essentially, it's only the degree 2 and higher terms that will affect concavity if you're dealing with a polynomial. So, what's our goal? Well, it's never undefined. So we set it equal to 0. We can factor out 60x squared. And if we do, we'll get x squared minus 2x minus 3. Well, that's a little bit more convenient to factor. That factors as x minus 3 times x plus 1. All right, good, good. So what do we see? Well, our potential inflection points are at 0, at 3, and at negative 1. So we just sketch our line, negative 1, 0, and 3. Now we go in and we figure out what's happening. So we pick some numbers. Say we pick a big number like 4. Now remember, this is y double prime, so positive, positive, very positive. Okay, so that says y double prime is positive. How about 2? Well, positive, negative, positive. So we're going to flip our sign. Negative. How about negative a half? Well, positive, negative, positive still. So we're still negative. How about negative 2? Negative, negative, still positive. And so we're back to positive again. You'll notice here, we mentioned this before. See how 2 has this, it's an even number, x squared. That says at 0, we don't actually change the sign. If you were to sketch the curve, it would come down and it would, well, actually it would do this. It's negative, comes up, and comes back down. So the curve, that the second derivative looks something like that. And we don't change the sign. So it's the even power we touch but don't cross. The odd powers we cross. We flip the sign. So looking at this, we can say, okay, what do we have? Well, when are we concave up and concave down? If we're concave up, that means y double prime is greater than 0. So concave up from where? And the answer is from 3 all the way out to plus infinity. All right, how about concave down? Well, wait, there's another part, concave up over here. Let's take care of that part. So this is also concave up. And that's from negative infinity up to negative 1. And by the way, of course, you could also have written this as negative infinity, comma, negative 1, and 3, comma, infinity. And we're never going to test on what notation you use. That's fine. And the endpoints, well, there's a little bit of disagreement depending on whether you ask the book or a faculty member. So we're never going to test on the endpoint. All right. Now we come to this interval. Well, notice we're negative and negative. So we're concave down and we're still concave down. So what we can do is we can actually glue the two of these together and say that we're concave down for that whole interval. So from negative 1 up to positive 3. So in other notation, negative 1 up to 3. Now you might say, the reason you might say, wait a second, how can I be concave down at 3 and concave up at 3? That doesn't make any sense. We shouldn't include the endpoints. But remember, when we're talking about concavity, we're talking about comparisons. See, concavity isn't about what's at a particular point. Concavity is about what's in a particular interval. And so when we talk about something being concave up at a point, what we really mean is around the point, it's concave up. So at 3, you could say it's neither concave up or concave down at 3. It's only when you say 3 in relationship to the numbers above it that we include it being concave up. All right. Well, now let's do 2 examples, which might be a little bit controversial, depending upon whom you ask. But of course, I'm the one asking. So let's see what we get. Find the inflection point, or possibly points, for f of x equals x to 1/3. Now, this is the cubed root of x, and it's not so hard to draw the cubed root of x. It looks a lot like you draw x cubed on the side, because it is like you draw x cubed on the side. In particular, this is the inverse function of x cubed. And we can even just look at it. And we can say, oh, look, over here, that definitely looks concave down, because, if you think of it like a bowl, concave down is a bowl that would spill your water. And over here, well, that's concave up. And we say, sweet, so that should be 0. Looks like a fairly good candidate. Well, let's see what the math says. Well, f prime of x would be 1/3 x to negative 2/3, and f double prime of x would be negative 2/9 x to negative 5/3. Well, it's undefined at 0, so that's a potential point. So mark 0, and if you plug it in, you'll see if I plug in a positive number, I'll end up with a negative. So that matches with the picture. If I plug in a negative to a negative power like this will be negative times another negative means that it'll be positive over here. And so everything's feeling good. Feels like 0, should be an inflection point. Let's come back to that in a second. All right, how about this one? Well, f prime of x, that's 2/3 x to negative 1/3, and f double prime of x, that'd be negative 2/9 x to the negative 4/3. Yes? That sounds right. Now what happens? Well, if you sketch number line, you'll see because of this even 4 upstairs, that whatever you plug in, as long as it's not 0, because you can't plug in 0, this part will always be positive, and so we're negative, and we're negative. Now the temptation is to say, oh, wait a second, can't we just say concave down everywhere? Isn't that true? Isn't it? Isn't it? All numbers? Now let's sketch the curve and think about whether or not that's true. It looks something like that. And it's certainly true that it's concave down over here. And it's certainly true that it's concave down over there, but it's not concave down everywhere. Why? Well, if you compare, say, a slope here, the tangent line, it's a negative slope, and a slope over here, it's a positive slope. I can't be going from a negative slope to a positive slope and be decreasing. So something is wrong. So, okay, so what's the common theme that's wrong here in both these problems? Well, there's an issue about how do you treat 0. And what it boils down to is that 0 can't be part of your answer. Because when we're talking about the inflection points, we're talking about the second derivative, which means I need to say what's happening with the first derivative, and the first derivative, 0, is undefined in both cases. And so I can properly say that here I don't want to talk about 0. So this would be a place where I would not include 0, because 0 is not part of the first derivative. And so similarly here, it's concave down from negative infinity up to 0, and it's concave down from 0 up to infinity, but we cannot merge them because of its being undefined, the first derivative being undefined at 0. Some people may say this is an inflection point, and it feels like it should be. And if you ask 5 different people, you'll get 5 different answers, and they'll hum and their haw. But, well, the moral is we should think a little bit about it. This is what mathematicians spend their time thinking about. Definitions. How do you interpret things? What could possibly happen? And, of course, it's also one of the things that makes it really hard to be a mathematician sometimes, because you always have to say, well, what if? What if? All right. So, well, enough with these potential what if type questions. Let's talk about something else. Let's use the second derivative. So we're going to talk now about what we call the second derivative test. It's a lot like the first derivative test, but it uses the second derivative, and hence its name. So it's not the second because it's the second test we were talking about. The second here really is referring to the second derivative. And again, this is saying, let's classify our critical points. Now, what's going to happen here? Well, our goal is we're going to say, hey, you know, the second derivative gives us information about the local behavior of the function. And it's telling us about how the first derivative is behaving. And so we can use that information to figure out what's going on. Now, in order to use it, of course, we have to have a place where the second derivative exists, which means that we have to have a place where the first derivative exists. So what are we looking for? Well, we're looking for a place where we have f prime of c equals 0. In other words, it's a critical point that we can apply a test to. And now we say, okay, what's true about f double prime of c? Well, the answer is there's 3 possibilities. It could be equal to a number that's negative, it could be equal to a number that's positive, or it could be equal to 0 itself. So let's sort of reason our way through what would have to be true. Suppose it was a number that was negative. What would that mean? Well, if we think about it in terms of a line here, here is our point C, and we know that f prime of c is equal to 0. And we know that f double prime of c is negative. Well, that tells us the following. Well, it tells us that our derivative is decreasing, which means that as I move from left to right, so as I move in that direction, the derivative goes down. So if I'm at 0 and I move this way, that says the derivative goes down, which tells me that f prime of c has to be negative on that side. On the other hand, I had to go down to get to 0. That tells me that f prime of c had to be positive on that side. So from the first derivative test, I can see I'm coming up, and then I'm going down, and therefore this is a max. Now, a second way to think about it is to actually draw the sketch. I say, look, here is my point C. f prime of c equals 0 says this is my tangent line. So here's my tangent line right there. And remember the picture. If our concavity is down, concave down, and that's what happens when we're negative, that says that we come down from the tangent line. So we're coming down from the tangent line, and now we say, oh, that's a max. Okay. So that's one case. What about if we're positive? Well, if we're positive, pretty similar arguments. So here's C. We say, look, if we're positive again, going left to right, if I'm at 0, f prime of c equals 0, that's our assumption, I have to go up. So my derivative has to increase. On the other hand, I had to, somehow by going up, I had to get to 0, which means that in the front of c, I had to be negative. So I'm going down, then I'm going up. So if I'm down then up, well, that means first derivative test says this is a min. Okay, but again, we can sketch the picture. Here's C, here's f of c, here's the tangent line because it's 0. And remember, here we're concave up because positive. So when we draw in the curve, it's going to come off the tangent line in the upside, above it. And that's at a minimum. Now what about 0? Well, the problem is lots of things can happen with 0. And so you don't have enough information. As an example, we could say x to the fourth at 0. That looks something like this. Negative x to the fourth at 0. Well, that looks something like you flipped it upside down. Or x cubed at 0. Well, that would look like that. All three of these have the second derivative is 0 at 0. And I suppose, to round it out, if we did negative x cubed, but you can see, we can either go up on both sides, we can go down on both sides, any combination. So anything is possible. So, in summary, here's what we do. If our derivative is 0 and our second derivative exists, then we say, look, if it's negative, the second derivative, local max. Second derivative positive, local min. And if second derivative is 0, more work. More work being the first derivative test. So, all right. Well, how do you remember that? The way I like to remember it is with the picture. This picture. Where my second derivative is positive, well, that says our curve looks like a smile. And therefore, we'd be at a min. If our second derivative is negative, our curve looks like a frown. That's a max. If our second derivative is 0, we have no idea what's going on, and we can't make any conclusions. Now, what test do you use? Well, the answer is you use the test that you're comfortable with, or you use the test that you're told. When you get a freedom, I would say it's usually often easier to work with the first derivative test for a couple of reasons. First off, you only have to take one derivative, and sometimes taking derivatives can be tricky. And the second thing is that it's more powerful, because when the second derivative test fails, the first derivative test often works. So you might say, why do we need the second derivative test? And the answer is, there are going to be times in the future when there won't be a first derivative test. And that means 1 year from now, when we're back all together talking about multivariable calculus, we're like, oh, we need that second derivative test. Okay, so let's actually do an example where we use the second derivative test. Use the second derivative test to classify the critical points of x cubed minus 3x squared minus 9x plus 15. Sounds a little bit familiar. So remember, this was the same curve we talked about a minute ago, so it's easy to take the derivative, but now, this time, we actually have to pay attention, and then we actually have to factor, and we'll see this factors pretty nicely. X minus 3, x plus 1, and now that tells us that our critical points are at positive 3, negative 1. So, take the second derivative. What will we get? 6x minus 6, same as before. So the second derivative at 3, that's 18, oh, got ahead of myself, 18 minus 6 is 12, positive. So what does that mean? Well, that says our second derivative is positive, which means that at 3, we have the smiley face. And therefore, 3 is and again, local min. Plug in -1. So we plug in, we get minus 6, which is -12. That's negative. What does that mean? Well, it means we have that frowny. Okay. And therefore, we can say that -1 is again, local max. So we don't have to test both sides. We just test at the point. And therefore, we're good to go. All right. Well, now that we know things like increasing, decreasing, concave up, concave down, we can put them together and talk about curve sketching. What is curve sketching? Well, I like to think about it industrial strength, connect the dots. Now, how do you plot a curve on a computer? Well, the way a computer does it, it says, I'm going to put in a couple thousand points. And those humans, foolish humans, they'll think that they see the whole curve. Because to them, it looks like you drew everything. But of course, they didn't. It just drew a few thousand points, and then it connected the points together. Well, we don't want to do a few thousand points. I mean, we want to be smarter than that. So we're going to try to be a little bit more methodical. So here we go. How do you do it? Well, the thing is, you want to find the good points, the ones that are somehow capturing the behavior. And the way you do that is you say, look, step 1, find all the points where the first derivative or second derivative are either 0 or undefined. So let's identify the best points. All right, so what happens here? Well, here we've actually done it. We just did this problem moments ago. So we know what's happening. So we know that the y prime equals 0. We did that. That's at -1 and +3. And we know that y double prime equals 0. That happens at, now we can figure that out. That happens at +1. All right, so reference here, I'm going to put y prime, that's 3x squared minus 6x minus 9, and y double prime, that's 6x minus 6. Okay, so now what we've done is we said, here are some really wonderful points. So the next step is say, okay, now that you have where the points are going to happen, let's actually draw where the points are in the picture. So we need real points. These are x coordinates right now. So we need to get the full coordinates. So let's see. So -1, if we plug in -1, that'll be a -1, then the -3, and a +9, and a +15. So -4 plus 24 should give us 20. If we plug in +3, we'll get 27. Subtract 27, that's good. -27, lots of 27s here, +15. So -27 plus 15, that should give us -12. And if we plug in 1, well, that's adding up the coefficients. 1, -3, that's -2. -9, that's -11. Plus 15 should be 4. So we're going to come over here, and we're going to sketch those points in. Now, of course, to help us see the picture, we're not going to put this quite to scale. Okay, so we'll say, mark some points here. So let me. So I'm going to somehow compress it in this way. So I'm going to think of these ticks as being 5 in the y direction, and these ticks as being 1 in the x direction. So for example, -1 and 20, I would put as here. 3 and -12, I would put that roughly here. And 1, 4, I'd put right there. Okay, So here are my important points. And now you're thinking, whoop. But remember, we have to do more. Okay. Next step. Determine the sign of f prime and f double prime between each pair of points. So, in particular, notice I have 4 intervals. So, between each pair of points, it actually means including the negative infinity and the positive infinity. So here we go. We should, let's do it down here. So I'm going to have negative 1, positive 1, positive 3. And now we've actually done some work. So for example, the second derivative, we said it changes sign at 1. So we know that if we're bigger than 1, our second derivative is positive. So y double prime is positive, and here also positive. And if I'm below 1, I'm negative. Y double prime, negative, y double prime, negative. How about the first derivative? Well, okay, that maybe we should think a little bit about, but we're not going to think too hard, because this factors, that's 3 times x plus 1 times x minus 3. And we say, okay, pick some numbers. Say a big number, like 4. That's a big number. Plug it in. You'll see that the first derivative is positive. Now at 3, that's going to be a place where we change sign. So if you plug in 2, you'll see that this term at the end becomes negative. So then y prime is negative. How about from negative 1 to 1? Well, notice 1 is not a root. So we're not changing behavior of the first derivative. So the first derivative is the same behavior from negative 1 to 3. So I'm still negative. So y prime is still negative. See, negative 1 is where I change behavior. Plug in a number like negative 100. These two are both negative. So the result is it's positive. Now, why is this important? Well, let's take a moment to just talk about our shapes. So I'm going to cover this up for a second so we can talk about our shapes. So there's essentially 4 possibilities when it comes to our shapes. So we could have that y prime is negative, or we could have that y prime is positive. And then we could have that y double prime is negative, and that y double prime is positive. So what does this mean? Well, y double prime is negative means we're concave down, so that's the frowny shape, but we also need to have that the derivative is decreasing, which means that we have that kind of thing going on. So it's coming down like that. Here, we're still saying that, you can see our slopes are negative. Over here, we're still frowny face, but our slopes are positive, which means that we're having that type of behavior. Concave down, but increasing slopes. Now, suppose y double prime is positive. That means it's a smiley face shape. If the first derivative is negative, that means that we're coming down. So that says our function has to look something like this. And if our derivatives are positive, because these have negative slopes, if our derivative is positive, that means we're coming up like that. Okay? So we can tell our basic shape if we know the signs of the first and second derivative. So in particular, if we just sort of use our key here, y prime being positive and y double prime being negative, that says roughly what are we at? Okay, if y prime is positive and y double prime is negative, that means that in this interval we have to be doing kind of this kind of shape. If we're both negative, that means we have to sort of having this kind of shape. Now, if the first derivative is negative but the second derivative is positive, that means we're having this kind of a shape. And if we're both positive, that means that we're having this kind of a shape. So the information about the first and the second derivative is really information about what's the behavior of the curve, what's the shape of the curve. And that's good to know. So that was this third step, is trying to understand these basic pieces. Now the last step is to draw a good picture. Now let's take a couple things into account. The critical points, that's where we have a slope of 0. So I'm going to just draw in a dashed line, saying there's my tangent line. So whenever I come into those lines, I have to come in with a 0 slope, and I have to leave with a 0 slope. So, putting this together, what do we get? Well, for the first part below -1, we're going to come up into here, and so we have to look something like that. Between -1 and 1, we have to come out 0 slope and head into that point. And now we're coming in, out, and so we're coming something like that. Roughly speaking, it's not going to be perfect, but that's okay. And now for the last part, we're coming out, and we're going to have a nice shape, something like that. So our cubic looks roughly like this. Is it precise? No. Is it pretty good? Yeah. For only drawing a couple of points, it's actually a pretty good estimate about what the curve would look like. And so we saved ourselves a lot of work, and we captured a good amount of the behavior. Well, let's try one like it. Another one. Sketch y equals 2x over x squared plus 4 and mark any local max, min, and inflection points. So remember, what are we after? Well, we need to know the first derivative and the second derivative. So, here we go. We have y equals 2x over x squared plus 4, y prime. So that would be a quotient. We take the bottom times the root of the top minus the top times the root of the bottom all over the bottom term squared. What does that give us? Well, that gives us 2x squared plus 8 minus 4x squared, all over x squared plus 4, quantity squared. And if you simplify that, which we probably want to, that will give us 8 minus 2x squared divided by x squared plus 4, quantity squared. Now, that's the first derivative. Let's do second derivative. Y double prime. What is that? Well, again, take the bottom, x squared plus 4 squared times the root of the top, negative 4x. And then we're going to take that, subtract the top, 8 minus 2x squared, times the root of the bottom, which is 2 times x squared plus 4 times 2x. We've got to do the chain rule. All over the bottom term, x squared plus 4 squared, squared. So that'll become x squared plus 4 to the fourth. Now, one thing we can do to simplify this right from the start is we can cancel off a single x squared plus 4 off of every piece. So we get down to there. And now we'll distribute what we have left upstairs. We'll have minus 4x cubed, and then minus 16x. Then we have minus 8 times 2 times 2x. So that would be minus 32x, I believe. Minus 2x squared times 2 times 2x. And so what will that be? Well, that'll be a plus 8x cubed, all divided by x squared plus 4, quantity cubed, which at the end becomes, well, notice everything has an x in it, so we can factor that out. These two terms would be combined together. Originally it would be 4x cubed, but we factor an x out, so that's 4x squared. And then we have minus 16x minus 32x, which is minus 48x. All divided by x squared plus 4, quantity cubed. So, there we go. Our function, our first derivative, and our second derivative. Now, what do we need? We need to find all the points where the derivative is 0, or the second derivative is 0, or undefined. Now, x squared plus 4 in the denominator is always positive, so we don't have to worry about undefined. What about equals 0? Well, for the derivative, we just worry about the numerator. That tells us that x squared has to equal 4, which tells us x equals plus or minus 2. down here, again, we'll set it equal to 0. That says either x equals 0. Whoops. Ha ha ha. We forgot to factor out the x. Check your work. Check your work. Okay, so we get here x equals 0, or x squared has to equal 12, which means the square root of 12, well, plus or minus 2 square root of 3, because 12 is 4 times 3. So now we're ready to get some estimates, or at least some points. So we found all the points where f prime and f double prime are 0. Let's actually talk about where these are at. Now, by the way, square root of 3 is about 1.7-ish. We can use that as an estimate here. So this is really about 3.4-ish, give or take, plus or minus. All right. So let's go through and list. We have a total of 5 interesting points. What are they? Well, they're at minus 2 root 3, minus 2, 0, positive 2, and then, of course, positive 2 root 3. Now, we can actually save ourselves a little bit of work. Certainly 0 is easy to do. We get 0. But notice something about our function. It's a little bit odd in that it's odd. It's an odd function. So if you plugged in a negative x, you get the negative as if you plugged in the positive x. Which means if we plug in the positive, and let's say we plug in positive 2, for instance, upstairs we get 4, downstairs we get 4 plus 4, which is 8. So when we plug in 2, we would get 1/2. Well, that means if we plugged in negative 2, we would get negative 1/2. We can do that without even having to think too hard. How about 2 root 3? Well, if we plug that in, if we square it, we get 12 plus 4 is 16. Upstairs we'd have 4 root 3, so that would be square root of 3 over 4. So that means if we plugged in here, we'd get negative square root of 3 over 4. Now, again, 1.7, square root of 3 over 4 is 0.4-ish. Okay, give or take. So we come along here, and we mark our points. So we have, let's see, let's make this 0, 1, 2. Let's see, 1, 2, 3, 4. That should be enough. 1, 2, 3, 4. That should also be about enough. And we actually don't even have to go up very high. It's not going to go up very far in either direction. So let's say we'll make this 1/2. Let's make this 1/4. I'll make this 1/2. So make this negative 1/4. And make this negative 1/2. Just so we can see what's going on. So we get the 0, 0. Then we have 2/2. So 2/2 would be here. And of course, negative 2, negative 1/2 will be over here. 2 root 3. Again, that's about 3.5, give or take. Let's see, 3.5 would be about here. Root 3 over 4. Well, it's a little bit less than 1/2, not quite 1/4. We'll say it's roughly here. So by symmetry, that'd be this one. Would be roughly right about here. There we go. So there are the interesting points. Now we have to say what's happening to our derivatives and our second derivatives. Well, so we have to make a table here. Okay, so here we go. So minus 2 root 3, minus 2, 0. Here's at 2. And here it is at 2 root 3. So let's talk about our first derivative. Our first derivative is only going to change signs at 2 and negative 2. So if I pick a point above 2, and I just need to look at the numerator, something above 2, let's say 3, I get 8 minus 18. That's negative. So our first derivative is going to be negative over here. Now between negative 2 and positive 2, I can pick 0. I can see I get 8. That's positive. So that my derivative will be positive between negative 2 and positive 2. And now if I pick a number like, say, negative 3, because I'm squaring it, I'm going to get the same result as what I did over on that side. So I'm back to being negative. How about the second derivative? Well, second derivative, where do I change signs? I change signs at 0 and plus or minus 2 root 3. So again, I can think I pick a big number, like 100, just a ridiculous number. So I get 100, and I get this massive number minus 48, which is going to be a huge number. And therefore, my second derivative is going to be positive over here. Now, between 0 and 2 root 3, I can pick an easy number like 1. So I'll get 1 times 4 minus 48, which is negative, which says that between 0 and 2 root 3, my second derivative is negative. Now, between 0 and negative 2 root 3, plug in negative 1, I'll get a negative here, and then over here I'll get a positive again. Wait a second, did I do this right? So I should flip my signs here. Yes? Okay. So I plug in negative, negative 1, that'll be negative, and that'll be negative, which means I'm going to be positive. Yeah, so y double prime is positive, y double prime is positive, and if I plug in, say, negative 100, that's negative. That'll be a huge positive number, minus 48. So the whole result is that we're negative. Okay. So what is this telling us? Well, it's telling us that, so negative, negative, what does that mean? It means that we come down. Then here, we're negative, positive, which says that we're this shape. Okay, negative, positive, 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 means we're doing this. Positive, negative, means that we're doing that. Negative, negative, wait a second, did I get that right? That's, yeah. Negative, negative, that means that we're going to have that. And then negative, positive, well, okay, concave, up, decreasing slope means we're going to have that. So these are, whoops, sorry about that. These are our basic shapes, what we're going to look like between the points. Now one last couple notes. We know that these are where the derivative is 0, so those are tangent lines. The other thing is, asymptotically, 2x over x squared plus 4, as x gets large, I'm going to have to approach this line. So for large x, I'm going to approach that line. So we now understand we're coming off here, we go down into that point, and then from here we come up into our place. So this is a place where our derivative is 0, and then we're going to come up, and now the rest of it is symmetry. We're going to come up into here, then come down into there, and then we change concavity and go back towards that line. And that's the shape of the curve. So here is our max, here is our min, there's an inflection point at there, at the origin, and again over there. And that's the curve. How close is it? It's actually really close. Very, very close. Of course, we had to work on it, but it's a lot better than having to plot 10,000 points. I hope it is. Otherwise, I should quit my job and become a computer. No. It is better than plotting 10,000 points. All right, let's do one final example. So let f of x equal e to the x cubed minus 1. Use linearization at x equals 1 to get an estimate for f of 1.05. Now use concavity to determine if this is an overestimate or an underestimate. Were we too big or were we too small? Well, let's use linearization. Of course, linearization is just a fancy way of saying tangent line. So I take my function f of x, which is e to the x cubed minus 1. And now I want to find f prime of x. So that would be chain rule e to the x cubed minus 1 times the derivative of x cubed minus 1, which is 3x squared. Now we want to use linearization at 1, which means the tangent line at 1. So we're going to find f of 1. Well, that's e to the 1 minus 1, that's e to the 0, which is 1. While f prime of 1, that's e to the 0 times 3 times 1 is 3. So we have that our linearization is equal to f of 1 plus f prime of 1 times x minus 1. So that's equal to 1 plus 3 times x minus 1. And so our function at 1.05 is approximately what the linearization is at 1.05. And so it's approximately 1 plus 3 times 1.05 subtract 1. Well, that's 1 plus 3 times 0.05. And of course that's 1 plus 0.15. And therefore our answer is 1.15 is our estimate. Now there's a second sentence. It says use concavity to determine if this is an overestimate or an underestimate. So if I'm going to do concavity, I better take the second derivative. So f double prime of x, we're going to do the product rule, the derivative of the first, that'd be e to the x cubed minus 1. Then times the derivative of the x cubed minus 1, which is 3x squared. That gives us the second 3x squared, so we get 3x squared squared plus e to the x cubed minus 1 times the derivative of 3x squared, which is 6x. So we plug in 1. What do we get? Well, we're going to get 1 times 9 plus 1 times 6, which is 15, which means that we are concave up at x equals 1. So our tangent line, we actually can figure that out. See, we pass through the point 1, 1, we have a slope of 3. So our tangent line looks like this. The concave up tells us that the function is going to come up on the upside of the tangent line. So whatever the function does, it's up above the tangent line. Well, that tells us that if I come over here to this point 1.05, that the function is above the tangent line. So are we an overestimate or an underestimate? And the answer is that the function is over our estimate. So we are below. So this is an underestimate. So we could probably say it's not going to be 1.15, it's going to be bigger than 1.15. Now we can even go further and say, well, if we had information about the second derivative, we can even get a better estimate for one. Instead of 1.15, we can use that information. And that's going to be a wonderful topic that we're going to actually cover next semester. Calculus 2. Beautiful topic called Taylor polynomials. But for today, we're done. That's it.